Good teachers embrace their role as data collectors. After all, your primary goal is to ensure that students are learning. Now, good assessments, such as well-constructed quizzes and tests, are a good start, but you need to know how to interpret that data to make sure that students are meeting and exceeding your expectations. Statistics are used to better understand data. In this module, we'll give you a brief introduction to the statistical concepts that are most valuable to a classroom teacher. Now, the online written portion of this module will help you understand how to interpret statistical results. But after the tutorials in this short module, hopefully you'll find that calculating the statistics doesn't have to be difficult either. Once you're in the classroom and you give a quiz or test, you'll find that as soon as those tests are graded, the students have two immediate questions. First of all, how did the class do as a whole? And secondly, how did they do? And these are actually the two most common uses of statistics. First of all, to determine how values are similar, which is also called the central tendency of a data set. And secondarily, how values are different, which is called the variance of the data set. We'll deal with both of them, but let's start with central tendency. The central tendency of a data set is a single number value that describes the set as a whole. This is the answer to the student question, well, how did the class do on the test? There's a couple of different ways you can answer this, and the most commonly used techniques to describe central tendency are the mean, the median, and the mode. Before we get too involved, let's go ahead and take a look at a data set. Let's say that you as a teacher just gave an exam, and these are the 11 scores that were earned by the students. Now, I know that most class sizes are larger than 11 students, but for the sake of illustration, we'll keep the data set small. The average test grade, which is also referred to as the mean test grade, is pretty easy to calculate. All you do is add up all of the data values and then divide by the number of values that you have. By the way, in official statistical speak, the number of values that you have is called the population size. So in this example, divide 887 by the population size of 11. The mean test score is approximately 80.64. You could also describe this set of data using the median. Now, the median is the middle value of the data. To make things easier, I'm going to put the data values in order first, from lowest to highest. There are 11 data values in this set. 11's an odd number, so that means this data set will have a middle number, in this case, 84. You can tell it's the middle number because there's 5 data values that are less than 84, and 5 data values that are greater than 84, so 84 is right smack in the middle. Calculating the median is not much more difficult if there's an even number of data points. Take a look at this data set. It's the number of excused absences per student for a class over a school year. This time there's an even number of data values, 12 to be exact. So once again, before we calculate the median, let's put those data values in numerical order from lowest to highest. Let's choose the two numbers that are in the middle of the data set, 7 and 9. The median is the average of those two values, 8 excused absences per student. A third measure of central tendency is the mode. The mode is the data value that occurs most often in a data set. Let's look again at the set of exam scores. 2 of the exam scores are 89, which means the mode of that data set is 89. Now, the excused absence data set is a different animal altogether. You could describe this data set as bimodal, because there are actually 2 modes. Notice that 2 students had 12 excused absences, and 2 students had 6 excused absences. When you've got a bimodal data set, it could mean that you're measuring 2 different things. It might be helpful to examine a histogram or a bar chart of this data. To be unscientific for a moment, we could say that this graph looks as though it has 2 humps. It seems as though there are 2 distinct groups of students in the class, one that has fewer excused absences than the other. In this example, these are the excused absences of a class during the last period of a high school day. Half of the students are involved in varsity sports, and the other half are not. Because those sports are required sometimes to travel to away games, and this travel time often occurs at the end of the day, the portion of the students involved in sports tend to have more excused absences. So with just a little investigation, we've discovered the reason for this bimodal data set. Not only are we measuring the number of excused absences students have, we're also actually determining who is and isn't involved in after-school sports. In this case, the mode was useful because it showed some sort of division between our students that might actually affect achievement as well. But enough about the mode. Let's go back for a moment to the mean and the median. And specifically, let's look at the mean and median of the test scores example. The average of the test scores was approximately 80.6, but the median was 84. Sure, those numbers aren't terribly different, but which is more accurate? Which better describes how the class did? If we look closely at the data, we see that one of the test scores is significantly lower than the others, 52. If this 52 were even lower, it wouldn't change the median. However, it would change the mean. Quartiles can be used to further split data, in a manner not too different than the median, which split the data in half. In fact, quartiles split the data into quarters, hence the name. Let's look again at the data set of exam scores. To identify the quartiles, let's let the median split the data into two separate data sets, each of which has 5 values. Let's look at the lower 5 values. The median of this 5-value set is the first quartile of the overall data set. Similarly, 89 is the third quartile of the data set because it's the middle value of these 5 numbers. By the way, the median is also known as the second quartile. Let's look at the data set consisting of excused absences. Remember, we used 7 and 9 to calculate the median. So, just as we did in the last set, we're going to ignore those values and allow them to split the entire data set into 2 halves. The first quartile of this data set is 5 because it's the middle number of these 5 values. The third quartile is 12, the middle number of these 5. Now, as straightforward as quartiles may seem, there is some controversy, believe it or not, about how to calculate them. In the examples that I just showed you, we excluded the median, or the pair of numbers that were averaged to create the median. Some statisticians would much rather you leave those values in when you calculate the quartiles, and that actually can change them. The interquartile range of a data set is very simple to calculate once you've identified the quartiles through whichever means you've chosen. All you have to do is subtract the first quartile from the third quartile. So that means the interquartile range for the test scores is 16. Remember a few moments ago, I told you that the mean of a data set can be affected by very high or very low values. And when compared to the other test scores, 52 is pretty low. The question is it low enough to be considered an outlier? An outlier is a data value which is so significantly different than the other data values that we say it's not representative of the data set. One way to identify outliers is to set up a range of expected values. You're essentially saying, based on what we observe in the data, all of the data values should occur within this range, and anything outside of this range is either suspicious or not representative of the group. To calculate the boundaries of that range, simply subtract the interquartile range from the first quartile and add the interquartile range to the third quartile. The interquartile range of the exam scores was 16. And the first quartile was 73. So we could say that any test score lower than a 57 is an outlier. Similarly, the third quartile was 89, so the upper bound of this expected value range is 105. Any values greater than 105 would be suspicious, considering that the highest possible grade on this exam was 100. Well, now that we've used a statistical procedure to determine that 52 is an outlier, does that mean we exclude it from the data? Remember, the sum of the test scores was 887. So if we exclude this outlying point by subtracting 52, then the mean of the remaining 10 test scores is 83.5, which is actually very close to the median of 84. By excluding the outlier, we've brought these two measures of central tendency into some sort of harmony, and it would probably be accurate to say the class as a whole averaged 83.5 or 84%. But it would be unethical simply to ignore this student who has scored so far out of the expected range. As an instructor, it's your job not just to report the scores so they make you look favorable, but also to use the results of this statistical analysis to determine who needs extra help and what might be going wrong. And this 52% is a big red flag. Before we wrap up this section on central tendency, let's take a look at 2 very common ways that data is displayed. Let's pull some of the descriptive statistics from our test score data set, specifically the quartiles, the median, and the max and min values. And we might as well pull this outlier too. If we plot these values on a number line, and then draw a rectangle whose sides are the quartiles, we've created a box and whisker plot. The box, by the way, contains the entire interquartile range, and the whiskers extend to the max and min values of the data. And by the way, If you subtract the minimum value of the data from the maximum value, you get the range of the data. So at a quick glance, you can identify both the range and the interquartile range. The median is this vertical line here, inside the rectangle. A box and whisker plot is a quick way to get a look at how spread out the different quartiles are. Outliers are typically included as an asterisk on a box and whisker plot. So in this case, we'll put an asterisk at 52, the location of our outlying data point. A stem and leaf plot is another quick way to visualize the dataset. You may elect to use this very traditional means by which to assign letter grades. The first digit of the score represents the letter grade. Except for 100, any grade that begins with a 9 is an A, anything that begins with an 8 is a B, etc. Let's sort these exam scores according to the first digit. Now we'll call this first digit the stem, and the second digit of each exam score the leaf. For instance, there are two A grades, a 92 and a 94. To create the stem and leaf plot, we use a stem of 9 and then two leaves, a 2 and a 4. You create the leaves by leaving off that first digit. Similarly, there are 5 grades in the 80 to 89% range. So that stem is 8, and the leaves are 0, 4, 8, 9, and 9. Basically, we've created a horizontal version of a histogram. The longer the branch that holds the leaves, the more students that earn that grade. Variance describes the spread or the variability of the values in a dataset, how different the data values are from one another. Let's take a look at a new dataset, a set of 8 exam scores. Take my word for it, the mean of this data is 79. To calculate the variance, we're going to take each of these values and subtract the mean. For example, the first value is 80, so 80 minus the mean of 79 is 1. You then take each of these differences and square them, and then add them together. In this case, you'll get a grand total of 450. Finally, you want to divide by the population size, which is 8 in this case. The result is 56.25. Therefore, the variance of this dataset is 56 2500ths. The square root of the variance is called the standard deviation of the data. When it comes to variance, standard deviation is the most commonly used measurement. The smaller the standard deviation, the more compactly the data points are bunched together near the mean, and the larger the standard deviation, the more spread out the data is. For example, let's take a look at another data set of 8 values. Again, you'll have to take my word for it, but the mean of this data set is also 79. But you may notice at a quick glance that the values in the new data set are a bit more spread out. If you were to calculate the variance of the new data set and then take the square root, you would get a standard deviation of 14.29, which is nearly twice the standard deviation of the original set. So our hunch is confirmed. The second data set appeared to contain more variance, and the first data set appeared to be more clustered near the mean, and according to the standard deviation values, both conclusions are true. To speak a little bit more about the standard deviation, we need to first discuss distributions. A data distribution is related to the histograms we talked about earlier. It's a quick way to visualize where all of the data values in a set lie. A data distribution that looks like this is said to be left skewed, or negatively skewed, because its median is greater than its mean. The opposite of that would be a right, or positively skewed distribution, in which the median is less than the mean. If a distribution is not skewed, it's described as normal, and is often referred to as a bell-shaped curve. Bell-shaped or normal distributions are of particular interest when it comes to standardized or norm reference tests. For example, let's say you're taking the SAT test. The score that's reported to colleges is not the total number of questions that you got correct, which is sometimes called a raw score. Rather, it's a standardized score, or a scaled score, that's been fitted to the normal curve. Let's use the critical reading section, formerly called the verbal section, of the SAT as an example. Once the scores are normalized, the mean critical reading score will always be 500, and the standard deviation is always 100. By the way, the minimum and maximum scores on the critical reading section are 200 and 800 respectively, each 3 standard deviations from the mean. Therefore, a score of 650 is between 1 and 2 standard deviations above the mean. Because SAT scores are normalized, you can draw very specific conclusions. including something called the 68, 95, and 99.7 rule, or the 3 sigma rule, which states that 68% of all normally distributed data values lie within 1 standard deviation of the mean, 95% of the data lies within 2 standard deviations, and 99.7% of the data lies within 3 standard deviations of the mean. How likely are you to score an 800 on the critical reading section of the SAT? If 99.7% of the data lies within 3 standard deviations, that leaves 0.3% of the population that is scored beyond 3 standard deviations from the mean, either extremely high or extremely low. We want to calculate only the extremely high scores, so divide that 0.3% by 2 to get 0.15%. Only 0.15% of the students that take the SAT get an 800 on the critical reading section. Before we wrap up, I want to speak for just a moment about a new movement in educational statistics called value-added assessment. This movement is gaining steam in educational circles, and you're bound to hear it mentioned, so here's a quick primer on what it all means. In short, value-added assessment uses student standardized test scores before and after a school year to determine how a specific teacher, school, district, or curriculum affects learning. Let's say the students that will be in your classroom next year score 1.5 standard deviations below the mean on standardized exams. After a year with you as their teacher, let's say they score half of a standard deviation below the mean. These students are literally exhibiting below average achievement, but we can tell that their achievement increased a great deal because of the time spent in your classroom. All students in similar classes should have similar curricula, similar expectations, etc. However, value-added assessment gives insight into what you, as an individual teacher, achieved with that group of students. Your instructional presence in the room added value in the form of a full standard deviation increase in test scores. In summary, we've shown you a few ways to organize and interpret data, and we encourage you to actively investigate the steady stream of numbers that flow into your grade books each and every day. Like it or not, we live in a world of educational accountability, so make sure you understand the methods by which you and your students will be assessed, and conduct ongoing assessments of your own instruction to make sure you're maximizing your effectiveness in the classroom.